So Professor Christis Chrysostomou, he will be discussing the assessment and retrofit of reinforced concrete structures. He's a full professor at the Cyprus University of Technology, coming from the Higher Technical Institute in Nicosia, where he stayed from 1990 to 2007. Well, as many of the previous presenters, his interests and his expertise focus on earthquake engineering with analysis and design of structures, as well as in situ measurement of the dynamic characteristics of structures and monuments, and also health monitoring. So he's also been a member that was very much involved on the development of the Cyprus Seismic Code, representing Cyprus in the Technical Council of FIB, and of course in the technical committees for the Eurocodes. Professor Chrysostomou, thank you very much. Please do proceed.
Yeah, okay, thank you very much for the introduction. What I'm going to do is present the assessment and retrofit of reinforced concrete structures, as it was mentioned before. So it's the material part. Now we are starting with concrete. So first I will present the scope of clause 8, then present the identification of geometry details and materials, structural modeling, resistance models for assessment, verification of limit states, and resistance models for retrofitting.
Devo cambiare?
Is it okay? So the codes that I have been using is the ones shown here, and pretty much are the ENQ versions for part 3 and part 1.2. The formal vote version of part 1.1 of 1998, and formal vote for 1992 part 1.1. The scope of clause 8. Clause 8 contains specific criteria for the assessment of reinforced concrete structures in their present state or for their upgrading if necessary. 8.2 gives information on what data should be collected and rules for knowledge levels, complementary to clause 5 for buildings, and for bridges, one has to use 12.42. 8.3 and 8.4243 gives rules for structural modeling of reinforced concrete structures, complementary to those of 6.3. And then we have 8.42, which gives resistance models for assessment of existing members in terms of generalized deformations. 8.43 and 8.44 give resistance models for assessment for existing members and joints respectively in terms of shear. And then 8.5 gives the rules for verification of the limit states, complementary to those of 6.5. And 8.6 gives resistance models for retrofitting of existing structures as the ones that Professor Kappos mentioned. I just wanted to say that the numbers above 2 clauses or sub-clauses refer to EN 1998 part 3. When references to other clauses are made, then the particular code is mentioned. So for the user to apply the code, the following steps may be followed. First, start from 8.2 to collect information and establish the knowledge level, then proceed to 8.3 and 8.4243 for the structural modeling, obtain the resistance models for assessment of existing members in terms of deformation from 8.42, obtain resistance models for shear in critical zones and joints from 8.43 and 8.44, and obtain the safety verification requirements from 8.5. And in case that strengthening is needed, then the models in 8.6 may be used. So regarding the geometry, this is something that Paolo presented before. We have to specify details about the geometry, details of the reinforcement and material properties. And then 8.2 states the minimum requirements that should be collected regarding information, in addition to 5, so as to be able to perform a proper assessment of an existing reinforced concrete structure. And for bridges, again, 12.42 should be applied. This information is used for structural modeling, the resistance models, and in addition, the partial factors on resistance. There is a knowledge level for each of the three attributes: geometry, construction, and material properties, where 1, 2, and 3 corresponds to minimum, average, and high knowledge. Then definitions of these knowledge levels and how each one is attained for geometry and construction details are given in 5, and Paolo mentioned a few things. While for the materials, then in each material chapter from 8 to 12, more information is given, and for reinforced concrete structures, this chapter is or subclause is 8.24. The selection of knowledge level depends on the availability and detail of the original design documents, and on the extent of the survey, which can be limited, extended, or comprehensive. Again, Paolo mentioned that, so I'm not going to go into details about this, but this is outlined in chapters 5 and 8. So the next item is the percentage of elements, and again, this is something that was covered before. I'm just putting this for completeness, so as for somebody who has the presentation to be able to follow in this way. And as Paolo said, here, depending on the limited, extended, and comprehensive, then the percentage of elements to be checked can be obtained. And this is a way to move from one level of knowledge to another level of knowledge in case that we are interested in doing that. Now, let's go to the structural modeling. So here it is stated in the code that the member stiffness for linear and initial stiffness for nonlinear analysis should be that of a second value at yielding. And of course, in order to do that, you need the yield moment for the axial load resulting from the gravity loads concurrent with the seismic action, and the corresponding core rotation at yielding. And the member stiffness may be taken to be equal to the mean value of that ratio, my times LV divided by 3 theta y of at the two ends of the member. And the simplification for the initial analysis was also mentioned by Tatiana before, that it can be taken as 25% of the gross, so as at an initial stage to do this calculation without requiring to do the detailed calculation. Now, the resistance models is the next item, and in this clause we have resistance models for beams, columns, and walls under flexure with or without axial force, beams, columns, and walls verification of shear and critical zones, and beam column joints. Starting with the first one, a paragraph was set in this clause saying that verification in bending for beams, columns, and walls which have not yielded in the seismic situation associated with the limit state considered may be carried out using ECA Part 1.2, Clause 10 in the case of buildings, or ECA Part 2, Clause 6 in case of bridges. So, and this is sort of a simplification that was required so as not to do all the verifications using the chord rotations. Regarding then the formation capacity and rotation for members that have yielded should be defined in terms of the chord rotation as defined in ECA Part 1.1.7.1. As Tatiana mentioned, most of the material that was here in ECA Part 3 was moved into ECA Part 1.1 so as to be used also for new structures. So the chord rotation is defined as the angle between a tangent at the member end and a chord which is connecting the two ends of the member. Here we see it for a cantilever, for a beam, and for a structure. The ultimate chord rotation, and this is something again that was being mentioned before, of an existing member is given by formula 8.1, where is the summation of the chord rotation at yield and the plastic part of the chord rotation multiplied by a coefficient A bars. This formula was also transferred into part 1.1 as a separate formula without the A bars, so as to be used for new members. And A bars here is being used is a reduction factor less or equal to 1, accounting for the type of bars where there is ripped or smooth, and lap splices if any. Now, the rules for the deformation capacity of the members are given for members with continuous ripped bars. For members with ripped bars lap spliced at floor levels, and for columns with smooth or plain bars lap spliced at floor levels. Again, it is stated that for large walls, which are classified according to EC8 Part 1.1, the verification may be done with EC8 Part 1.2 subclause 10.9. Now, the chord rotation at yield may be evaluated using the equations that were moved in EC8 Part 1.1. And there are equations for rectangular columns, for walls of any cross-sectional shape and member with hollow rectangular section, and for circular columns. It should be noted that here the first part of the equations accounts for the flexural contribution. The second term represents the anchorage slippage of bars, and the third the contribution of shear deformation. The factor to be used for the ripped bars, A bars is equal to 1, and the plastic part of the ultimate chord rotation may be calculated from formula 7.5, which is shown here, which is basically calculating first or estimating what is the basic value of the plastic chord rotation, which was determined for a member which is detailed for DC3, for zero axial force, for symmetric reinforcement concentrated at opposite ends of the section, and a concrete strength equal to 25 megapascals, and then for a shear span to depth ratio of 2.5. And then for that particular case, depending on what type of member we have, it takes these three values that we see here. And then the other coefficients, then these are modification coefficients which modify depending on the conformity on the ductility class, for the axial loads, for the asymmetrical reinforcement, for concrete strength different than 25, for a shear span different than 2.5, and for confinement. So using this formula, one can arrive at TU plastic. Now, it is also stated that for members of any cross-sectional shape, including circular, not covered by paragraph 2, then theta U plastic may be calculated from formulas 7.6 and 7.7, where here the curvature, the ultimate curvature, phi U, the yield curvature, and the plastic hinge length are used in order to arrive at TU plastic. In this particular case, strains are defined for calculating the ultimate curvature from section analysis for both confined and unconfined concrete, and also formulae are given for calculating the plastic hinge length, and one formula is given for columns and beams consisting of rectangular parts, walls of all types, and hollow piers. And the second one is for columns with circular cross sections of diameter D. Now, for existing structures, if the detailing of the members does not conform to codes for seismic design for ductility, then the plastic hinge length may be taken equal to 1.3 times the value given by equations 7.13 and 7.14. Now, for members with ripped bars, lap splice starting at the end section, what is being done in case that there is not enough lapping, and the minimum lapping is shown here, and this is what Paolo was mentioning before, then there are modifications in the capacity, and it's penalizing this by providing provisions and formulae so as to modify what we have said before regarding ripped bars which are continuous or they have adequate lapping. So the next item is columns with smooth bars lap spliced at floor levels. Here, the maximum stress at a vertical bar of diameter dBl can develop ahead of a standard 180-degree hook or bend is given by formula F0 and a correction factor there. So these two formulae can define that. And this stress is being used for developing the yield moment and chord rotations. So the clauses here prescribe how to calculate the yield moment for smooth bars with standard hooks and with straight ends, which is very useful because all structures that we have, some of them have straight hooks, especially in countries like Cyprus, that it was influenced by the British design. And then also equations are given for calculating theta y, which is a little bit different than what we have seen before, and also the effective stiffness, and this is what I was referring to before when I was talking about the structural modeling. The next clause specifies how to obtain the ultimate chord rotation at the end of a column consisting of rectangular parts without or with lap splices by specifying the value of A bars to be used in Formula 8.1 in order to calculate the ultimate chord rotation, and theta u plastic can be calculated, as we have mentioned before, using the equations in EC8 part 1.1. Now, going to shear, this is something that has been changed. Mean values, of course, are being used again, but then what is happening now, EC8 part 3 directs to EC8 part 1.1, which in turn directs into EC2 part 1.1 for the calculation of shear, with some modifications that have to be used, which are specified in paragraphs 2 and 7 of EC8 part 1.1. The same approach is being done for beam columns. So shear now refers back to EC2 part 1.1, where the shear is calculated according to that code. So the next item is verification of the limit states, and we start with beam columns and walls under flexure with and without axial force. And for the near collapse, again, we are going to divide the calculated ultimate chord rotation by gamma RD, whereas it was mentioned by Paolo, gamma RD accounts for uncertainty in the ultimate deformation by considering the uncertainty of all parameters involved in the corresponding formulae of 8.4 and those in 8.6 relating to each retrofitting method. And values for primary members of gamma RD are given to in 3 to 4 to 5, while for secondary members, gamma RD equal to 1 should be used. Now, in the case of ripped bars, continuous or with lappings longer than LOU mean in the plastic hinge region, the code directs to table 10.2, which provides the total logarithmic standard deviation of the resistance model required to evaluate the partial factor. So these are the ones, total logarithmic standard deviations that can be used for the chord rotation. And according to the note and the formula that was shown by Paolo, then gamma RD can be calculated using this equation with AR bar 0.85, the total logarithmic standard deviation from table 10.2, and then using the appropriate target reliability, where for NC and CC2 is 2.33, and using that value, then the chord rotation theta u gamma RT factors come out to be 1.55 and 1.4. And as it was mentioned by Paolo, they are a little bit higher than what we are used to, but we have to remember that we are using here mean values compared to characteristic values. So 3, the paragraph 3 also gives the logarithmic standard deviations for ribbed bars with short lappings, and 4 and 5 for smooth bars with hooks and straight ends, which can be used in a similar manner in order to obtain the gamma RD factors. It should be mentioned that the target reliability factors are NDPs, so each country can specify its own. And then there is the whole process, and that's why I'm showing it here. In case that these are modified, then one can modify also the partial factors in EC8 part 3. For the limit state of significant damage, the chord rotation capacity corresponds to significant damage to be used for verification should be assumed to be a fraction of the ultimate chord rotation. And this was mentioned also by Tatiana, so I'm not going to spend time on this. And therefore here the same values are being used, 0.5 and 0.35, to change, to take part of that plastic rotation to add to the yield part of the rotation to do the verification. And of course, it has to be divided by the corresponding partial factor, which is going to be different now because a different reliability index is going to be used, which is going to be equal to 1.6. And therefore, the partial factors for the SD are 1.35 and 126. In 8511, the reliability, the logarithmic standard deviations can be used for the rest of the combinations that we have for smooth bars and all the others that we have in order to calculate the gamma RD factors. Now, regarding the damage limit state, damage limitation limit state, here, so that deformations remain in the elastic domain, the bending moment should be limited to the yield moment under the design value of the axial load. And this is the requirement that is being placed there. Now, going to beams, columns, and walls in shear, again, the capacity or the resistance is going to be divided by the gamma RD factor, and logarithmic standard deviations are again given for the calculation of the partial factors at the NC stage, and for secondary members, gamma RD should be taken as 1. Verification against significant damage and damage limitation is not required unless one of these two limit states is the only one to be verified, in which case we have to apply 85.21. For beam column joints, for the limit state at near collapse, then design shear force is evaluated depending on whether the summation of the moments of the beams is less than the summation of the moments of the columns. And in that case, two equations are given for calculating this design horizontal force, one for interior joint and the other one for an exterior joint. And if the reverse is happening, in other words, if we have the summation of the beams larger than that of the columns, then equations 8.25 and 8.26 are used to calculate and design shear, and that one is verified against the resistance, which is calculated, as we have mentioned before, using actually EC2 part 1.1. Verification against the exceedance of significant damage and damage limitation, as in the previous case, is not required unless one of these is the only one that we are going to check. And then we go to the resistance models for retrofitting. Again, partial factors should be used and calculated as we have mentioned before. The first method is concrete jaggeding, and the purposes of concrete jaggeds are described here in detail. And then the simplifying assumptions for the purpose of evaluating the strength and deformation capacities of the jaggeded columns or walls are given in this subclause. The equations that were shown also by Professor Kappos before are the ones to relate the values of VRMY, theta y, and theta u, which are calculated under the assumptions of 1, to the values, the star values, which are going to be adopted in the resistance verifications. And as Professor Kappos said, here, the introduction of the axial load is introduced in these factors, which is a new thing for the code. Now, in steel jaggeding, steel jackets may be applied in columns for the purpose of increasing shear strength and improving the strength of deficient lap splices. And their shear strength may be calculated using equation 8.31, and provided these the steel jaggets remain elastic, then this resistance in shear can be added to the one of concrete that already exists in the existing member. And also there are some provisions regarding clamping of lap splices that specifies what has to be done in order to achieve the clamping of the lap splices. And then we go into the FRP plating and wrapping. The externally bonded FRP may be used for the enhancement of the flexural resistance, the shear resistance, of the available ductility, and also prevent the lap splice failure. Again, I go through what is provided here is the beam columns and walls under flexure with and without axial force. And then we have continuous rib bars. In the same manner that it was done before, this is the highest, let's say, capacity. And then if we go to lapped or members with smooth bars, then there is a reduction in the capacity. So as we say here, theta y is calculated as we have shown before. And then theta u is calculated with A bar equal to 1 again, but theta u plastic now is taking into consideration the contribution of the FRP. So the K confinement is changed, and the same formula is used to calculate theta u plastic. Again, it is allowed for members of any cross-sectional shape, including circular wrap in FRP, to calculate theta u plastic using formula 7.6. And strains are given to be used for calculating the ultimate curvature in this clause here. And also it is stated that the plastic hinge length can be calculated from formula 7.13 and 7.14 that we have seen before. For now, ribbed longitudinal bars, lap spliced, again, we apply whatever we have with modifications to take into account that. The first modification is the lap length at yield, which is using a new formula, and LOU minimum, beyond which ultimate cord rotation is not reduced, may be calculated using formula A2, but using parameters that are specified in this subclause. Again, theta u may be calculated using 8.1 and theta u plastic from 7.5 by specifying a different confinement coefficient, again specifying here how this is being done, and also lap slide, the lap length, and also the L that is going to be used in the formulas can be calculated using 7.13 and 7.14. For smooth bars, again, we apply what is applied for without FRP, and then we have modifications for the calculation of the F0, the stress, by changing ASW in order to take into account the contribution of the FRP. And finally, regarding the ultimate chord rotation, a new formula is given here, which applies for longitudinal bars that are continuous, and a second one for the case of longitudinal bars that are spliced in order to be able to calculate the ultimate chord rotations for these members. And finally, for shear resistance, the shear resistance of brittle components, columns or walls, we can use FRP strips, either by fully wrapping the member, or in the case of beams, by bonding them to the sides and to the soffit of the beam, as shown in this diagram. And the shear resistance contribution is considered as the sum of the contribution from the existing reinforced concrete member and that of the FRP, which can be calculated using the formula at the bottom. This was my presentation. I had to go a little bit fast. I tried to show everything that we have in the code, more or less, with references, so as to be easier for somebody if he wants to follow it. And I thank you for your attention.
Thank you very much. There have been no specific questions added. There's only one question that has been added in the meantime that I would say would be posed to any of the presenters, perhaps, of this first half, that is related to the fact that should new and existing elements of the same structure be designed with different target betas. I don't know if someone wants to comment on this. Paolo, I see you shaking your nodding.
Yes, I saw the question in the chat.
Yes.
No, the target reliability is defined for the whole structure, and it is defined in not for different members, but yeah, for the whole structure in part 1.1. And there is an explicit statement, which I recall during my presentation, that says that a relevant authority, for his own reason, might reduce for existing structure. So it's explicitly said that the existing structure, as a compromise, because there is no other reason, as a compromise, might be allowed to target a lower reliability. Then the differentiation of reliability might come in terms of consequence classes, no? Because the structure is different in terms of use, in terms of importance, but not because a member is new or existing. Once the new member is added to the structure as a whole, that structure as an organism has to fulfill a given reliability target. I think the answer is that so the beta is not unique, but it's not differentiated element from element.
Yes, makes
sorry, yeah, okay. At parity of mechanism, of course. Like, you know, brittle could be granted an extra protection and so on. This is two members, formations, same targets.
As you had also mentioned in your presentation, the fact of the different...
Should be clear. So let us say it twice.
Okay, so we are indeed almost 25 minutes behind schedule, so we should be restarting at 4:25. So I discussing this with Rita, we were thinking of shortening the break to 5 minutes, more or less.